So let's see what happens when we have unsymmetrical carbonyl compounds. So here I have an example of, I've got 2-methylcyclohexanone, and at the alpha position on one side I've got a tertiary hydrogen, at the alpha position on the other side I have secondary hydrogens. So let's take a look at what will happen and start examining the mechanisms and how we can drive this reaction towards one or the other product. So first I'll draw what we would get if we remove the tertiary hydrogen. Okay, so removal of the tertiary hydrogen leads us to this enolate. Then let's look at what would happen if we remove the secondary hydrogen. So now if I remove the secondary hydrogen, and I've color-coded them so we can kind of keep track of it a little bit easier, we get this enolate. That's removal of the secondary hydrogen. So now as I compare those two enolates, okay, I can look at this alkene here and say that this alkene is more substituted alkene. So then if I compare that to this one, this is the less substituted alkene. So that makes this product more stable, and this one less stable. So we've talked about these before, stability in products. That makes this one the thermodynamic product, because the more stable product is always going to be the thermodynamic product. So the other piece of it that we have left is that here at the secondary position we actually have two hydrogens. So there are two secondary hydrogens. Well, over here there's only one tertiary hydrogen. Also, if I look over this side, there's less steric bulk around here because on this side I've got a CH3, where on this side I don't have any CH3 that could be blocking the base to come in to pull off one of these hydrogens. So there is less steric hindrance on this side, while on the other side there's greater steric hindrance. So if I look at these two and figure out which one is easier to get the proton off, there's two equivalent protons here versus one, and there's less steric problems here versus the tertiary side, so this will be the kinetic product. It's faster to form and easier. So the more substituted alkene, more stable, will lead to the thermodynamic product, whereas more equivalent hydrogens and less steric hindrances will lead to the kinetic product. So I hope by now you would think of this without me even asking, but what do organic chemists want to do? And the answer is, of course, that they want to control everything. So the next thing we need to look at is how can we control to specifically get the kinetic enolate, and then after that we'll look at how can we control to specifically get the thermodynamic enolate. So if we want the kinetic enolate, what we want to start with is a very strong non-nucleophilic base. And it has to be non-nucleophilic because we've just spent the last two chapters looking at what happens if we have a carbonyl and we introduce a nucleophile. It'll either do a nucleophilic acyl substitution or it will do a nucleophilic addition based on whether or not we have a good leaving group. So we need to make sure we have a non-nucleophilic type base. And this assures that the enolate will form rapidly. And also the larger the bulky base, makes it harder to remove the proton at the more substituted carbon. Secondly, we want to have low temperature. And a low temperature will prevent equilibrium. And equilibrium, of course, will always favor the more stable product. So if we can avoid equilibrium, we can form our kinetic product. And the last thing that we want is a polar aprotic solvent. The polar part is good because that helps it to dissolve and dissolve the polar reactants. And stabilizes the intermediate. If the intermediate is stabilized, that will lower the activation energy of the reaction. And we want it to be aprotic so that the enolate doesn't get reprotonated, which will allow for equilibrium. So for the thermodynamic enolates, we want a strong base still, but not quite so big. So now this time we might use something like sodium ethoxide, versus up here where we might want to use something like LDA that has the two big isopropyl groups on it. So this is a much smaller base, which will allow it to get in and deprotonate either side, including the side that is more substituted. As far as temperatures, we want something like room temperature, which actually in a lot of reactions is quite a lot of energy. And at room temperature, this can allow the reaction to reach equilibrium, which will of course favor the thermodynamic product, or the more stable product. And last, now we want a polar protic solvent. This allows the enolate to be deprotonated and reprotonated over and over. So the enolate forms and is reprotonated repeatedly, once again allowing for equilibrium, which favors the more stable product. So examples here might be something like methanol or ethanol, water. A good example of a polar aprotic solvent might be something like THF, tetrahydrofuran, or ether, diethyl ether. Example of temperatures, so room temperature versus low temperature. Low temperature might be minus 78 degrees C, which is driest in acetone, or 0 degrees C, which is water and ice, versus room temperature, which we typically say is 25 degrees C, even though that's probably warmer than a lot of our labs are, but that's standard room temperature.